Section: Introduction. In this section, we discuss the impact of sequence generation models, especially those based on the transformer architecture, which have transformed various fields by allowing models to generalize beyond their training data. Large language models, for instance, can tackle new tasks by interpreting a text description and a few examples without needing to adjust their parameters, a process we refer to as in-context learning. This ability is particularly useful for meta-reinforcement learning tasks, where we aim to create models that can generalize to new tasks. Recently, there has been a focus on in-context reinforcement learning, ICRL, which seeks to develop general meta-RL solvers with scalable architectures similar to large language models. However, training these models in real time can be impractical and potentially unsafe. Offline pre-training can improve ICRL by removing the need for risky online interactions, which is crucial in areas like robotics and healthcare. Despite this, current offline ICRL methods have significant limitations. Approaches like algorithm distillation and decision pre-trained transformer have shown potential in offline ICRL, but they do not explicitly optimize the RL objective of maximizing cumulative reward. This gap poses challenges in offline RL tasks, where achieving optimal behavior is essential. While some recent studies have looked into scalable online ICRL, they often depend on various heuristics and have not been tested in the more complex offline settings. Our primary aim is to explore whether methods that focus on optimizing the RL objective can yield better results in offline ICRL and if these improvements are consistent across different scenarios. Specifically, we seek to answer several questions. 1. Does optimizing the RL objective enhance performance in offline ICRL? 2. How does the quality and coverage of offline datasets affect this optimization? 3. Are specialized offline RL techniques necessary for effective offline ICRL? 4. How do algorithms perform when we only have a collection of data without learning histories? 5. Can RL effectively manage a mix of dynamics and out-of-distribution dynamics? To address these questions, we conduct an empirical study using over 150 datasets from popular GridWorld and MuJo tasks. We compare various RL-based methods with algorithm distillation, a strong supervised baseline, to assess the impact of explicitly optimizing for reward in offline ICRL. To our knowledge, this is the first study to focus on optimizing the RL objective in an offline ICRL context using a scalable transformer architecture. In the realm of offline reinforcement learning, our goal is to train agents to maximize rewards using pre-collected datasets without interacting with the environment. This approach presents unique challenges, especially in managing out-of-distribution state action pairs. We test widely accepted offline RL baselines in the offline ICRL setting to highlight their advantages as reward maximization algorithms. For discrete environments, we utilize conservative Q-learning and implicit Q-learning, while for continuous environments, we apply IQL and the straightforward TD3 plus BC method. A key trend in offline RL involves using transformers to model trajectories through supervised learning, as first introduced by decision transformer. However, subsequent research has shown that these supervised methods, which do not focus on reward maximization, often struggle with low-quality datasets or those lacking problem-solving trajectories. They find it difficult to connect suboptimal trajectories into optimal policies, a challenge that can be overcome by methods that directly optimize RL objectives. Our intuition suggests that similar issues may arise in offline ICRL when reward maximization is not prioritized, a notion supported by our experiments. Algorithm distillation has been a significant advancement in scalable in-context RL, utilizing transformer architectures to learn an improvement operator by distilling information from the training histories of single-task agents across various environments. However, it assumes access to complete training histories, which may not always be available. In our work, we show that RL-based methods can utilize datasets more effectively, particularly those with low-quality demonstrations, and manage unstructured data better. The decision pre-trained transformer focuses on predicting optimal actions from historical data and a given state but relies on having an oracle for optimal action sampling, which is often impractical. Our tested RL-based methods do not require access to such an oracle. Neither algorithm distillation, decision pre-trained transformer, nor their subsequent modifications optimize RL objectives during offline training. This oversight can lead to suboptimal policies, as these methods adapt supervised learning techniques to the offline ICRL setting without addressing the core goal of reward maximization in RL. Recent works like Imago and Relic have explored scalable in-context RL by incorporating off-policy RL techniques, outperforming algorithm distillation and decision transformer in online settings, but they have not been tested in offline environments. The unique challenges of offline RL, such as the inability to interact with the environment, make the direct application of online methods less effective. This highlights the need for offline-specific methods that explicitly optimize RL objectives. Furthermore, we demonstrate that strong performance can be achieved without complex modifications, contrary to the reliance on numerous implementation details in Imago and Relic. Section Summary. In this section, we discuss the transformative impact of sequence generation models, particularly transformers, on meta-reinforcement learning, RL, through in-context learning, emphasizing the need for offline pre-training to enhance safety and applicability. We aim to investigate whether explicitly optimizing the RL objective improves performance in offline ICRL and explore various factors affecting this optimization, using empirical studies across multiple datasets to compare RL-based approaches with existing methods. Section: RL Incorporation. In this section, we utilize algorithm distillation, AD, which is a transformer-based model, as our baseline. The goal of AD is to predict the next action based on the learning history, where each step is represented as a combination of the current state, the previous action taken, and the previous reward received. We combine these elements into a single token. While we keep the same transformer structure as AD, we make several changes to integrate reinforcement learning, RL, objectives. Specifically, we enhance the input tuples with flags that indicate whether an episode has ended and the current step in the episode. We also replace the next action prediction with value function heads that are trained using RL loss functions. For continuous problems, we add a policy head as well. We evaluate 3 RL methods for discrete environments. Twin Deep Q Network, DQN, which is a straightforward RL method. Conservative Q Learning, CQL, a common offline RL approach that emphasizes value function pessimism. And Implicit Q Learning, IQL, a well-regarded offline RL method known for its effectiveness across various tasks. We adapt IQL for natural language processing tasks by adding the CQL term to the IQL loss in discrete settings. Additionally, we conduct tests in continuous environments using TD3 as our online baseline, along with its minimalist TD3 plus BC offline modification and continuous IQL. During inference, we use the maximum value operator to predict actions for discrete methods. We label all RL methods with the prefix IC in context, such as ICDQN, ICCQL, ICIQL, ICTD3, and ICTD3 plus BC. For our experiments, we primarily use 2 environments: dark room, Doctor, and dark key to door, K2D. Doctor is a discrete Markov decision process, MDP, while K2D is a partially observable MDP, POMDP. Both environments consist of a 2D grid where the agent can move in various directions or stay still, only observing its current position. These environments are popular for scaling experiments within our limited computational resources. We also introduce a modified version of DR for additional experiments and test popular continuous mu-Jo co-environments, including half-cheetah-vel, HCV, ANT-dir, ANT, Hopper params, HPP, and Walker 2D params, WLP. In DR, the agent starts at the center of the grid and must find an unknown target to earn a reward of 1. In K2D, The agent begins at a random spot, needs to locate a key, reward, 1, and then reach a door, reward, 1, both of which are also unknown. Episodes in both environments end when the task is completed or after a set number of steps. In HCV, the agent runs at a fixed unknown speed, in ANT it navigates to an unknown point, and in HPP and WLP, the agent must move quickly while avoiding falls, with system parameters like gravity being randomized. For DR, we use a 9x9 grid with an episode length of 20 and a 19x19 grid with an episode length of 100. In K2D, we test a 9x9 grid with 50 steps per episode and a 13x13 grid with 100 steps per episode, allowing us to assess performance across varying complexities. The Mu-Jo co-environments are limited to 200 steps. For discrete environments, we gather training histories using the Q-learning algorithm, adjusting the number of histories per target goal, 1 or 5. We create datasets for DR 9x9 with 70, 40, and 20 training targets, for DR 19x19 with 300, 150, and 75 training targets, and for both K2D versions with 1,000, 500, and 250 training goals. For continuous environments, we collect learning histories from 100, 50, and 25 instances using the Soft Actor Critic (SAC) algorithm. To evaluate data quality, we divide the trajectory datasets into 3 expertise levels, early, mid, and late, by splitting the original datasets into 3 equal parts. We name the datasets using a specific format that includes the environment name, grid size, number of training targets, and number of histories per target, with the absence of an expertise level indicating the full dataset. For instance, DR 9705 refers to a dataset from the 9x9 doctor environment with 70 training targets and 5 histories per target. Additional details about the datasets can be found in the appendix. Section Summary. In this section, we utilize Algorithm Distillation (AD) as our baseline and modify its transformer architecture to incorporate reinforcement learning (RL) objectives, evaluating various RL methods like ICDQN, ICCQL, and ICIQL in discrete environments such as darkroom and dark key to door, as well as continuous environments like half-cheetah-vel and ANTDR. We design experiments to assess performance across different complexities and data quality levels, using specific datasets derived from our environments to analyze the impact of training histories on RL outcomes. Section: Evaluation. In this section, we evaluate the performance of our trained policies by running each policy over 100 successive episodes in both discrete and continuous environments. We track performance at 25, 50, and 100 episodes and calculate the normalized area under the curve, NAUC, to provide a single value for comparing agents. This metric captures performance trends over episodes and is less affected by noise than fixed episode evaluations. By monitoring performance at specific episodes, we can identify convergence rates and any potential declines during rollouts. We use NAUC to select the best hyperparameters, as detailed in the appendix. For the discrete reinforcement learning (doctor) environments, we assess all target goals not included in the training set, while for other environments, we use a fixed set of 100 random test targets that are separate from the training data. To ensure robustness, we follow a specific evaluation protocol, employing different random seeds for hyperparameter searches and final evaluations. In our experimental results, we first compare the overall performance of selected methods in discrete environments, demonstrating the effectiveness of the NAUC metric. We then analyze performance across key offline reinforcement learning dimensions, such as data quality and coverage. We also explore the implications of not having access to learning histories, which may not always be possible in real-world situations. Additionally, we test the ability to learn in mixed dynamics and handle out-of-distribution scenarios, conducting experiments in the challenging XLand minigrid environment. Ultimately, we show that the advantages of reinforcement learning extend to continuous environments. For our overall performance analysis, we utilized all available discrete datasets. The top graphs illustrate the average metrics for both test and training targets. In the dark room and dark key-to-door environments, we found that the methods maintained stable performance throughout rollouts, confirming that NAUC is a reliable metric for comparison. The bottom plots show performance profiles based on NAUC, revealing several key insights. First, reinforcement learning approaches consistently outperform algorithm distillation on average. While all RL methods perform similarly on training targets, there are significant differences on test targets. CQL achieves the highest performance on test targets, with an average improvement of 28.8% over algorithm distillation, followed by IQL with a 23.7% improvement, and DQN showing the least improvement at 16.6%. However, we did not optimize hyperparameters for DQN, which could enhance its performance. We provide tabular results for each dataset in the appendix, along with additional reliable metrics that statistically validate CQL's superior performance. These findings support our belief that optimizing the RL objective is essential for addressing ICRL problems. The performance gap between offline RL methods and the online-focused DQN highlights the benefits of offline RL algorithms in this context. It is important to note that we have limited hyperparameter tuning for RL approaches compared to algorithm distillation, suggesting that potential gains could be even greater with equal tuning resources. In our analysis of coverage, we examine how dataset coverage affects performance, a crucial aspect in offline RL. We assess coverage based on the number of unique training targets and the number of learning histories per target. While multiple histories are vital for algorithm distillation, they may not be practical in real-world applications. We analyze complete datasets across all environments, with NAUC scores displayed in the coverage figure. As anticipated, all methods perform better with increased target coverage and more histories per target. However, we observe significant performance differences among methods. Offline RL approaches generally outperform algorithm distillation, except in the DR9 datasets, where algorithm distillation slightly exceeds offline RL with 20 and 40 targets using a single history. DQN also averages better than algorithm distillation and surprisingly outperforms offline RL on DR19 tasks. In the more complex K2D environments, RL methods show greater resilience to the lack of multiple histories per target. For K2D, RL approaches perform comparably with 5 histories per target once sufficient target coverage is achieved, while algorithm distillation suffers a notable performance drop without repeated targets, highlighting its dependence on repetitive learning histories. The key takeaway is that RL-based methods are more data efficient than algorithm distillation and show greater tolerance for limited target repetition in learning histories, making them more suitable for real-world applications where complete coverage and extensive histories are often not feasible. Section Summary. In this section, we evaluate the performance of trained policies using the normalized area under the curve, NAUC, metric across various environments, demonstrating its robustness and reliability compared to traditional fixed episode evaluations. Our results indicate that RL-based methods consistently outperform algorithm distillation, particularly in terms of data efficiency and robustness to limited learning histories, making them more suitable for real-world applications. Section: Various expertise. In this section, we evaluate the impact of dataset expertise on offline reinforcement learning, RL. We analyze how different methods perform across datasets with varying levels of expertise. The complete datasets contain full learning histories, initially designed for AD. The mid datasets are a mix of low quality and nearly optimal trajectories, while the early datasets consist of easily obtainable low-quality data, and the late datasets feature near-optimal solutions. We present detailed statistics in the appendix, and the test scores for different dataset types are shown in a figure. We observe that AD struggles with early datasets, achieving NAUC scores below 0.4, while all RL methods perform significantly better. DQN stands out as the top performer, likely because low-quality datasets require less regularization, enabling the agent to seek higher rewards. CQL, which uses cross-entropy loss in discrete cases, acts as a bridge between DQN and AD, performing closer to AD when regularization is high, which limits its effectiveness on low-quality datasets. Although reducing CQL's pessimism could improve results, we did not test this due to computational limits. As expected, mid and complete datasets show similar performance trends, with AD remaining the weakest and CQL leading, followed by IQL. Interestingly, AD performs competitively on late datasets with high coverage, despite lower data diversity. DQN, however, underperforms on late datasets compared to offline RL methods, highlighting the need for offline regularization. Additional metrics in the appendix support these findings. Overall, our experiments indicate that RL methods outperform AD across various dataset expertise levels, but we note that tuning hyperparameters for offline RL methods to match data quality is an area that requires further exploration. Next, we address the challenge of lacking structured learning histories for algorithm distillation, which typically relies on multiple behavior policies collecting data for each task. To investigate this, we conducted experiments with randomly shuffled datasets, disrupting the sequential improvement that AD aims to distill. We also explored sorting randomly sampled trajectories by their discounted return values, which proved effective for some tasks, despite being sensitive to the discount factor. For these experiments, we used complete datasets from the DR19 and K2D13 environments, representing a more realistic scenario. Our results show that, on average, RL methods outperform AD with randomly ordered data, except for CQL on the DR19301 dataset. In the K2D13 environment, there is little difference among the RL methods, while DQN excels in DR19, consistent with findings on early datasets. When we sort unordered data by discounted return, offline RL methods consistently outperform both AD and DQN in the K2D environment. However, in DR19, only CQL maintains its performance lead, while IQL shows reduced results. Surprisingly, DQN and IQL perform better with randomly ordered data than with sorted samples in DR19, a phenomenon we cannot yet explain. Overall, CQL shows the best performance across different environments without access to learning histories, as further metrics in the appendix confirm. Finally, we explore how algorithms perform when trained on environments with different dynamics and then deployed in an environment with out-of-distribution (OOD) dynamics. We introduce a modified DR19 environment called Janus, where learning histories are collected from two instances of DR19, each with different dynamics. The training dataset includes behaviors from both dynamics, but no single history mixes them. After training, we deploy the agent in a grid where one half exhibits one dynamic and the other half the second dynamic. Our results indicate that when an agent is trained on both dynamics and deployed in an environment with only one, its performance is comparable across dynamics. However, when tested in an environment that combines both, performance drops, particularly for one dynamic, likely due to the asymmetry of the test environment. Ideally, a robust agent should perform well under both dynamics. Across all conditions, RL methods continue to outperform AD, with IQL exceeding AD by about 50% and DQN and CQL achieving roughly double AD's performance. In the Janus environment, RL methods maintain better performance under one dynamic and show slight improvements under the other. Offline RL methods do not provide benefits in this setup, as they are designed to avoid OOD state action pairs, which are unavoidable in Janus. Tabular scores are available in the appendix. Section Summary. In this section, we evaluate the performance of various reinforcement learning (RL) methods across datasets with differing expertise levels, finding that RL approaches consistently outperform AD, particularly in low-quality datasets where DQN excels. We also explore the impact of lacking structured learning histories and the challenges posed by environments with mixed dynamics, concluding that RL methods maintain superior performance compared to AD, with CQL showing the best results overall. Section X-Land Minigrid Evaluation. In this section, we evaluate our methods in the XLand minigrid environment to test their effectiveness in more challenging scenarios. We simplify our experiments by reducing the dataset size, selecting only one learning history per rule set and keeping just the first third of transitions. This results in a tiny dataset that is only 1% of the original size. Our performance results, shown in a table, indicate that reinforcement learning (RL) methods significantly outperform the alternative method, with their scores being about twice as high. Among the RL methods, DQN slightly surpasses CQL, while IQL performs a bit better than DQN. It's important to note that the original method achieved a mean performance of around 0.4 using much more data and more rollout episodes. This clearly shows that optimizing RL objectives is beneficial even in complex, data-scarce environments. Next, we extend our analysis to continuous state and action spaces, as many real-world applications, like robotics and autonomous driving, operate in these settings. We aim to see how our explicit RL objective optimization performs under the challenges of infinite state and action spaces. In our findings, we present performance profiles for various methods, including AD, the online RL method TD3, its lightweight offline version TD3 plus BC, and IQL. Consistent with our earlier results, the offline RL methods, TD3 plus BC and IQL, outperform AD in most cases, with AD only matching performance on datasets that reflect near-expert behavior. IQL is slightly behind TD3 plus BC on average. A notable difference is that the online RL method, TD3, performs worse than AD in continuous environments, likely due to the greater challenges of out-of-distribution states and actions. These results emphasize that incorporating offline RL components in ICRL methods not only enhances performance but also highlights the importance of the offline aspect in continuous settings. For more results and metrics, we refer to the additional plots and tables in the appendix.